Welcome to Computing Positional Accuracy. Our course objectives. First, we're going to start by going over a document from the Federal Geographic Data Committee, or FGDC. We're specifically going to concentrate on Part 3, the National Standards for Spatial Data Accuracy. This is where we get the formulas to compute positional accuracy. With the formulas out of the way, we're then going to show you how to compute positional accuracy from OPUS static reports, OPUS rapid static reports, RTK base and rover surveys, and also VRS surveys. Included as part of this training course, you will get a spreadsheet that allows you to compute positional accuracy. We're going to go into detail on this spreadsheet so that you understand how it works and how it can be modified as well. Finally, there is a test on positional accuracy for you to claim the associated number of PDHs, or professional development hours. The Federal Geographic Data Committee's document, Part 3, the National Standards for Spatial Data Accuracy. Down below this video, you will find Part 3, the National Standards for Spatial Data Accuracy. This document is where we get the formulas that are used to compute positional accuracy from OPUS rapid static reports and RTK or VRS measurements. Feel free to pause the video at this time to print out this document. Great, now that you've got the document printed out, let's go ahead and go to page 3-4. Once you find page 3-4, the National Standards for Spatial Data Accuracy uses root mean square error to estimate our positional accuracy. This accuracy is then reported at the 95% confidence level. Accuracy reported at the 95% confidence level means that 95% of the positions in the data set will have an error with respect to the true position that is equal to or smaller than the reported accuracy value. The question is how do we compute this accuracy value? To do this, we need to go to Appendix A, which is on page 3-10. This is where we get the formulas for computing positional accuracy. To compute horizontal positional accuracy, we're first going to need to compute the root mean square error both in the X and Y axis. To compute our root mean square error in the X axis, for example, what we will do is the root mean square error in X is equal to the square root of the sum of the X sub data, comma I, minus the X sub check, comma I. Notice those are in parentheses, so we'll take that difference and square it. We'll then add some squared answers together. We'll divide by n and finally take the square root. We'll do the same thing for the y-axis as well. Now, if you understand these formulas, raise your hand. If you don't understand these formulas, raise your hand. It doesn't matter, because what we're going to do is we're going to take these formulas and translate it into something we can relate to. For example, to compute your root mean square error in the northing, what you'll do is you will take the northing coordinates of your control point. You'll then subtract it from your northing computed coordinates. This comes from checking into your monument out in the field. We're going to have to check into our control point multiple times. We're going to take our northing published values, subtract it from our check shot, we're going to square that answer. And we're going to do that for every check shot we do. We're then going to add all the squared answers together. We're then going to divide by n, which is the number of times we shot that control point. Finally, we'll take the square root at the end to get our root mean square error for the northing. The same formula exists for the easting as well. Again, we'll take our easting control coordinates, we'll subtract it from our computed, which comes from checking into our control point out in the field. We'll take that difference, we'll then square it. You're going to have to shoot this control point multiple times. We'll take each one of those squared answers, we're then going to add them together. We'll finally divide by the number of times we shot that control point and then take the square root. Once we have the root mean square error in northing and easting computed, Now what we have to do is we have to look at those values because we have some scenarios for computing horizontal positional accuracy. If our northing root mean square error and our easting root mean square error is equal, to compute our horizontal positional accuracy, it is equal to 1.7308 times the value of your root mean square error in the northing or the root mean square error in the easting. It doesn't matter because it is the same answer. So take one of those values, multiply it by 1.7308, and you will get your horizontal positional accuracy at 95% confidence. Your other scenario is, well, if my root mean square error in the northing and my root mean square error in the easting is not equal, what we first have to do is we have to perform a ratio test. We will then take our smallest root mean square error number, we'll divide it by our largest root mean square error value, and if that answer falls between 0.6 and 1, then what we have to do to compute positional accuracy horizontally is we'll take 2.4477 times 0.5 times the addition of our root mean square error in the northing plus our root mean square error in the easting. To further explain what's going on in the second case where our root mean square error in the northing is not equal to our root mean square error in the easting, what happens is if we were to plot this out, what we're getting is an error ellipse. And if our ratio test falls between 0.6 and 1, then what this formula of 2.4477 times 0.5 times the addition of our root mean square error in the northing plus our root mean square in the easting, we're taking this elliptical error and we're making it circular error. The problem that part 3 does not address is when the minimum root mean square error divided by the maximum root mean square error is less than 0.6. It references a document called The Principles of Error Theory and Cartographic Applications by Greenwald and Schultz. And it states, when you look in this document, you can find where you may be able to use the same formula, the 2.4477 times 0.5 times the addition of your root mean square error in the northing plus your root mean square error in the easting. That Greenwald and Schultz document, especially pages 27 and 59, you may be able to go with lower ratio answers, but what we would recommend is, depending upon what your board of surveyors rules say and applying your own professional judgment, that's where you should be able to make your determination. If you are not comfortable with using lower acceptance ratios, then if your ratio goes below 0.6, it is advised that you go back out into the field and you re-observe the point. The Principles of Error Theory and Cartographic Applications is available at the bottom of this video. With our horizontal positional accuracy computed, to compute our root mean square error in the z-axis, we use the exact same formula. We'll take the z sub data comma I minus the z sub check comma I. We'll take those differences and square it. We'll add all the squared answers together. We'll divide by n, and finally we'll take the square root. To translate this to something we can better relate to, we'll take our vertical control point answers, we'll subtract it from our check shot vertical answers. We've got to do this multiple times again. Take each one of those squared answers, add them together, divided by the number of times we shot that control point, and finally take the square root. With that answer computed, to compute our root mean square error in the vertical component, what we have to do is we'll take 1.96 times our root mean square error in the vertical. To review, the Federal Geographic Data Committee's document, Part 3, the National Standards for Spatial Data Accuracy, is where we get the formulas that are used to compute positional accuracy from OPIS rapid static reports and RTK or VRS measurements. With the formulas out of the way, we can now put them into practical use. As we move forward in this training session, we're going to show you how to compute positional accuracy from OPUS static reports, OPUS rapid static reports, and from RTK or VRS measurements. By using Microsoft Excel, we're going to show you how to take the data with these formulas and enter them into a spreadsheet that can be used over and over again for computing positional accuracy for your jobs. Practical application of positional accuracy. With the theory and the formulas out of the way, we're now going to put them to use and show you how to compute positional accuracy from OPUS static reports, OPUS rapid static reports, and RTK and VRS measurements. In addition, as part of this course, there is a spreadsheet that has been included. This spreadsheet will show and automatically compute positional accuracy for you based on the different types of methods we've described. We're going to go over the spreadsheet and show you how it works and how you can modify it for your own needs. Down below this video, there are two Excel spreadsheet versions. One is for Excel 2007 and higher format, and the other is for Excel 97-2003 format. Please take the time to click on the appropriate zip file for the version you need and download it to your computer and unzip it. In addition, there are also OPUS static reports and OPUS rapid static reports included as well. Please go ahead and print these out, since we're going to be using these to demonstrate how the spreadsheet works. Calculating positional accuracy from an OPUS static report. To begin, let's review the process of OPUS static. What we need to make sure of is that we use a dual frequency GPS or GNSS receiver. We've gone out to the field and we've observed data continuously for a minimum of 2 hours up to a maximum of 48 hours. When we've done that, we'll come back into the office, we'll download our receiver, and our receiver file, more than likely, we're going to have to convert to a RINEX format. And then we'll go to the OPUS web page, the link provided here, to submit our results. When we go to the OPUS web page that is at the National Geodetic Survey's website, the first thing we've got to do is we've got to enter in our email address. This is where we want to see our results come back to us. The second step is to actually browse somewhere on our computer or a network drive to find that RINEX file for submission to OPUS. Then for the drop-down list, you want to select your antenna type, and then finally we'll enter in our antenna height. When you go to enter in your antenna height, it must be the true vertical measurement to the bottom of your antenna mount in meters, and this true vertical measurement to the bottom of the antenna mount could be called something to the ARP or antenna reference point. Because our data is greater than 2 hours and less than 48 hours, we'll click on the Upload to Static button. When we do that, now OPUS goes and starts computing our static solution. Just to make sure that we're all on the same page, the way OPUS static works is it takes the 3 closest surrounding core sites that meets the data criteria for OPUS processing, and what it does is it computes 3 individual baselines or vectors or radial shots, if you want to think about it that way, and then that answer is averaged together. Once we've gotten our solution back, now we need to start determining, do we have a good OPUS static report or do we not have a good OPUS static report? To begin, let's look at the header of our OPUS static report. Over on the left, we see the software that was used, we see the ephemeris that was used, the navigation file, our antenna name, our antenna height. Over on the right-hand side, we see the start time and stop time of our session, the number of observations that were used, the number of fixed AMB, which stands for ambiguities, that were used, and finally our overall RMS. Right here in this header section of our OPUS static report, we can start making a determination on if we have good results or not. A good OPUS solution, as some recommendations, your ephemeris should be either the rapid or the precise ephemeris. You should have 75% or greater of your observations that were used in your solution. You should have greater than 75% of your ambiguities fixed also in your solution. And finally, your overall RMS should be less than 3 centimeters. Finally, before you go away from your header, over here on the left-hand side, where you have your antenna name and your ARP height, this is a great time to double check to make sure that you selected the correct antenna type and entered in the correct HI when your results, when you were submitting your information to OPUS. Continuing on in a OPUS static report results, what we were getting to is we're getting to the meat and potatoes section of it. We have 2 reference frame columns. We have the NAT83 reference frame column with its datum tag, and then we have the ITRF reference frame with its datum tag. We're going to concentrate on the NAT83 column, and as we go down, we can see our answers in X, Y, and Z. We see our latitude and longitude, notice east and west, so it depends upon which way you leave Greenwich, England to get to your point. We have our ELHGT, that stands for ellipsoid height, and then we have ortho-HGT or ortho height, which we could think of as elevation. We can also see what vertical datum it's referenced to along with the geoid. Finally, we can see our coordinates of our points in both UTM and state plane with their respective zones. Notice these values are in meters. We get our convergence angle, our point scale factor, and our combined factor as well. If you notice beside your latitude, your longitude, your ellipsoid height, and your ortho height, we have a column of numbers. And these numbers represent something called peak-to-peak errors. And we're going to talk about what peak-to-peak errors are in just a minute. But we can make sure that these peak-to-peak errors fall within the criteria of a good OPUS solution, and a recommendation is to have your peak-to-peak errors less than 5 centimeters. To understand what a peak-to-peak error is when you went out in the field and you performed your OPUS session. When your data was processed, it solved a vector or a baseline to your receiver, and then it did the same thing from another course site and the same thing from another course site. Took all those answers and averaged it together. Well, what happens is you have different answers from each course site, and the peak-to-peak error is the difference from the low answer to the high answer. And we use peak-to-peak errors to compute our positional accuracy from OPUS static reports. Finally, continuing on with analyzing a OPUS static report, we have the base stations that were used in the solution and also the nearest NGS control point. To review, an OPUS static solution is an average of 3 core sites. The errors listed beside our latitude, longitude, orthometric height, and ellipsoid height are peak-to-peak errors. But our question is how do we compute positional accuracy from an OPUS static report? Well, the National Geodetic Survey provided these formulas for computing positional accuracy from OPUS static reports. To compute our horizontal positional accuracy at 95% confidence, we'll take our latitude peak-to-peak and square it. We'll add it to our longitude peak-to-peak value and square it. And then we'll take the square root of that answer, and that is our horizontal positional accuracy at 95% confidence. To compute our vertical positional accuracy at 95% confidence, it is the value that is listed beside it is our orthometric height peak-to-peak value. So whatever our answer is for orthometric height peak-to-peak, that is our vertical positional accuracy at 95% confidence. What we're going to do next is we're actually going to take our OPUS static report and we're going to use it with the spreadsheet to show you how we can enter these values to get these answers computed using the included spreadsheet with the video. Computing your positional accuracy from an OPUS static report using the spreadsheet. To follow along with the exercise, you can either watch it, or if you want to follow along, what you need to make sure of is that you've, over here in your left-hand table of contents, that you've downloaded the spreadsheet and you've also printed out the OPUS static report. If you need to pause the video to do this, feel free to do so now. Great, now that you've got everything ready to go, the spreadsheet's open, you got your OPUS static results, make sure that you're on the OPUS static positional accuracy tab. What we're going to do first is we're going to explain how this spreadsheet works, and then we'll start keying in the data. We have a column for our point name or number, and then notice how we have the units for metric, for meters, or U.S. survey feet, and for international feet. Notice for the U.S. survey foot and the international foot rows that we've already got zeros there. The reason why is because our OPUS static report gives us everything in metric, and the spreadsheet will automatically convert everything to U.S. survey foot units or international foot units. The other thing too is notice how we have zeros in our horizontal positional accuracy column and our vertical positional accuracy column. We don't want to touch those. That's where the magic's going to happen, and we'll show you the formulas that are in them as we get to it. Let's start by putting in some type of point name or point number. We're going to call it point 100. You can call it whatever you want. But then we're going to go to meters for the northern coordinate, and using our printed results, we're going to type in 232217.315, and if you click somewhere else, the spreadsheet will automatically convert your metric values to survey feet and also to international feet as well. Notice here in our survey foot column for the northern, we see up there in the formula area, we see what it's doing with our metric values. You can do the same thing for international feet as well and see the conversions that are going on also. Let's go ahead and fill out our easting value as well, which is 624,718.793. Then we'll go ahead and go over to our orthometric height column. Remember, that's our elevation. We're going to type in 117.387, and then we'll go over to our peak to peak for latitude or northing in this case. All we have to enter in now is the peak to peak errors for latitude, longitude, and the orthometric height, and the spreadsheet will go ahead and automatically compute your horizontal positional accuracy and your vertical positional accuracy. Our northern peak to peak errors is 0.014. Our longitude peak to peak errors is 0.018. As soon as we enter in both of those values, notice how you have your horizontal positional accuracy calculated. Then now we also can enter in our orthometric peak to peak, which is 0.046. And let's go ahead and put our cursor in the row for meters underneath the column for horizontal positional accuracy, what we've got highlighted here. And if you look up in the formula line, you can see where the square root is being applied. And then as you go down below that, you can see how we're converting that information either into survey feet or into international feet. If we go over to the row for meters underneath the vertical positional accuracy column, we can see that it's copying whatever we put in for our orthometric height peak to peak and computing our vertical positional accuracy at 95% confidence there. If you ran multiple OPUS static sessions for your job, then what you would need to do is you would need to highlight all of these cells and then right click on copy, and then we'll go down a row or so, and then we'll do right click and we'll go to paste. To reset the new values you just pasted so you can enter in another set of OPUS static results, you'd want to change your point number. Then you could actually, if you wanted to, using your delete key, you could delete only the row that corresponds for meters. So you'll delete your northing meters, easting meters, your orthometric height in meters, your peak to peaks, but don't go any further than that. Because if you were to do that if you were to delete this particular cell for the horizontal positional accuracy, you're going to delete the square root formula. Now you could do the same thing if you deleted it for vertical positional accuracy. You're going to mess up your spreadsheet, so you'd want to copy and paste again. Now you can go ahead and enter in your next set of OPUS results and get your positional accuracy computed. Hopefully we've explained to you how the spreadsheet works to compute positional accuracy from an OPUS static solution. Calculating positional accuracy from an OPUS rapid static report. To begin, let's review our OPUS rapid static field procedures. We're going to need to go out to the field with a dual frequency GNSS or GPS receiver. We're going to record data continuously for a minimum of 15 minutes up to a maximum of 2 hours. We'll then come back into the office, we'll convert our file to Rhinex, and then we'll go to the OPUS website to submit our results. At the OPUS website, we'll enter in our email address to begin with. We'll then go browse on our computer or on a network drive to where our Rhinex file is located and select that. Using the drop-down list, we'll select our antenna type, and then finally we're asked to enter in our antenna height. Notice that we're asked to enter in our antenna height in meters, and it needs to be the true vertical measurement to the bottom of the antenna mount, or it could be referenced to something called the ARP or antenna reference point. Now, once we click on our upload to static button, we can then go get maybe a cup of coffee, something to drink, a snack, and then hopefully 5 or 10 minutes later we've got our results back to us. Before we start looking at our results, we need to make sure that we understand how a OPUS rapid static solution is computed. When you use rapid static, it uses a simultaneous least squares adjustment of all the available data from up to 9 core sites that if it meets NGS data criteria, and if the 9 core sites are located within 250 kilometers of where you performed your field session. Knowing that, let's start looking at a OPUS rapid static report and breaking it down. To begin with, we're going to look at our header. We can see the software that was used. We can see the ephemeris that was used, the navigation file, the antenna name, and the antenna height or our HI. Over on the right hand side, we can see our start and stop time, as well as the number of observations that were used, something called quality indicators, and finally a normalized RMS. Right here in this header section is where we can make a quick determination on if we have good results and we should proceed. A good rapid static solution will again have its ephemeris being either rapid or precise, greater than 75% of the observations being used in your solution, and your quality indicators are greater than 3. Notice in your quality indicators you've got 2 sets of number with what you could think of as a divide sign. The first set of numbers is the quality indicator for where you performed your rapid static session in the field, and then the quality indicator, the second one here, is the quality indicator for the core sites that were involved in your solution. We want these numbers to be greater than 3. Finally, we have something called a normalized RMS, and we want that value to be less than 1. Continuing on in our OPUS rapid static solution, we've got 2 reference frame columns. Notice we have the NAD83 reference frame column with its datum tag, and then the ITRF reference frame column with its datum tag. We're going to concentrate specifically on the NAD83 column, where we see our results in X, Y, and Z. We see our latitude and our longitude, both east and west from Greenwich, England. Our EL height, that is ellipsoid height, our orthometric height or our elevation, and to the right of that you can see the vertical datum and the geoid that was used. You can also see going down as well the UTM coordinates and the state plane coordinates with their respective zones. Notice that these answers are in meters, our convergence angle, our scale factor, and our combined factor for our point. The values listed beside your latitude, longitude, ellipsoid height, and orthometric height are root mean square values. Because Opus Rapid Static uses least squares, these numbers here are root mean square values. Finally, continuing on with our Opus Rapid Static report, we see all the core sites that were used, and finally our closest NGS control point. To review, Opus Rapid Static uses least squares to come up with your answer. The errors that are listed beside latitude, longitude, ellipsoid height, and orthometric height are expressed to us as root mean square answers. Now, how do we compute our positional accuracy from an Opus Rapid Static, not static as it says here, it should say Rapid Static report? We're going to go back and use part of the Part 3, the National Standards for Spatial Data Accuracy, to compute our positional accuracy. Remember, once we had our root mean square error computed, if the latitude and longitude, or better yet, the northing and easting root mean square error was equal, we'll use the formula of 1.7308 times the root mean square error in the northing or the root mean square error in the easting. You pick one of those numbers, it doesn't matter because they're the same, to come up with your horizontal positional accuracy at 95% confidence. Now, if your root mean square error in latitude and longitude is not equal, remember we have to first perform our ratio test, where we take our smallest root mean square answer and divide it by our largest root mean square answer. And if that value is between 0.6 and 1, then we'll use the following formula to compute our horizontal positional accuracy. 2.4477 times 0.5 times the addition of our root mean square error in northing plus our root mean square error in easting. Again, you've got your ratio values. If you're not comfortable based on your board rules, if you go below 0.6, you may have to go out to the field and reobserve. Again, go back to the section on the Federal Geographic Data Committee to review what we've said about board rules and how you may be able to change this. What we're going to do now is to compute our vertical positional accuracy from our Opus Rapid Static report. We're going to take 1.96 times our orthometric root mean square error answer to get our vertical positional accuracy at 95% confidence. Next, what we're going to do is we're going to show you how to use the spreadsheet to compute positional accuracy from an Opus Rapid Static report using the samples that are included. Computing positional accuracy from a Opus Rapid Static report using the spreadsheet. If you want to follow along, what you'll need to do is make sure you've got your spreadsheet open and you've also clicked on the tab for Opus Rapid Static Accuracy. Also included were two Opus Rapid Static solutions. One where the root mean square errors were equal for latitude and longitude, and one where the root mean square errors for latitude and longitude were not equal. Make sure you've got all that. If you need to pause the video, feel free to do so now. Great. What we're going to do first is we're going to start with the Rapid Static report where our root mean square errors are equal, and those values are 0.006 for both latitude and for our longitude. So make sure you've got that sheet handy. To start with, we're going to go through and fill in the spreadsheet and explain what's going on. We're going to start with our point name or point number, and we'll enter that in. Notice that you have answers shown up or zero values showing up for survey feet or for international feet, and that's going to be based on the units you want to have. Also, don't start playing with the columns for root mean square error minimum over root mean square error maximum, your horizontal positional accuracy column and your vertical positional accuracy column, because this is where it's automatically computing your positional accuracy based on your root mean square error answers, and we'll show you that as we get further into it. Let's go ahead and enter in the metric northing for our coordinates. You can use state plane or UTMs, it doesn't matter which. We're going to use state plane. So we're going to do 232217.315, and when we do that and we move away from that cell, the spreadsheet goes ahead and converts it to either survey feet or international feet. Choice is yours. We'll do the same thing for our easting, which is 624,718.793. And then also we'll do the same thing for our orthometric height, which is 117.348. Once we've got those in, now we need to start entering in our root mean square error for both latitude and longitude. They are the same, so it should be 0.006 and 0.006. Once you do that, let's stop and see what's going on. Notice in the RMSE min over RMSE max column that answer is 1. And remember, based on part 3, that if the root mean square error in latitude and longitude were equal, then we need to use the formula of 1.7308 times, in this case, 0.006. And that's what the spreadsheet's done. So if we go ahead and go over to the min-max column for root mean square error, we can see that there's an if statement running here. And what it's doing is it's trying to figure out, okay, is one value greater than another value? And if so, we're going to take the smallest value and divide it by the largest value. If it's not, then it's going to go ahead and give us an answer of 1. Once we've gotten that determination figured, or that calculation, then if we go over to the horizontal positional accuracy column, we can actually see here the statement that's running. We have a double if-and statement. And the first thing that it does is it says, okay, after the if-and, if it says I3, which is the cell number, is greater than or equal to 0.6 but less than 1, then use the 2.4477 times a half times the addition of cell F3 plus cell G3. And cell F3 and G3 would be the root mean square error for latitude and longitude. It would add those together. If that case is not true, but if it is equal to 1, so we're going to the if, and then the I3 is equal to 1. So if column I3 is equal to 1, then it's going to use the formula of 1.7308 times F3. We just picked that when we wrote the formula. You could put G3 if you wanted to. It doesn't matter because it's the same value. If that case is not done, okay, so if it's not meeting any of that criteria, your spreadsheet right here for horizontal positional accuracy will give you the statement to reobserve. Let's go ahead now and fill in our orthometric root mean square error of 0.051, and we can see the vertical positional accuracy that was computed as well. If we go over to the row for meters and the column for vertical positional accuracy, we can see that it's taking the value in cell H3, which is our orthometric root mean square error, and it's multiplying it by 1.96. We can see now how the spreadsheet's working. We've got a second OPUS report to put in. So what we're going to do is we're going to highlight all these columns. We're then going to go ahead and right click and go down to copy. Somewhere down below we're going to right click and go to paste. When you do that, you can click somewhere, or you can press your escape key on your keyboard to get rid of that dash box. And what we're going to do is we're going to use our delete key to delete the answers out of the meters row And we're going to delete all the values up to and including the root mean square error for elevation. Notice we didn't go into the column for RMSE min over RMSE max. You don't want to go past that. Now let's go ahead and get out your second page, the one where the root mean square error for latitude and longitude is not equal, and let's start entering in those answers. Again, we're going to use state plane coordinates, so we're doing 232217.312. Then we're going to do 624.718.798. And then we're going to do for our orthometric height 117.381. And then we have for our latitude root mean square error 0.009. Our longitude root mean square error is 0.006. And our orthometric root mean square error is 0.049. And we can see here that the spreadsheet performed as it should have. Because if we look at the min-max column, we can see that it took the smallest root mean square error, 0.006, which was for longitude, and divided it by the largest root mean square error, which was latitude, 0.009, and it came up with our ratio answer of 0.67. That fell within our ratio specs, and we now can go ahead and compute positional accuracy from that. If you have made a determination based on the Greenwald and Schultz document and your interpretation of your board rules and through consulting through your board, if you need to change or lower your ratio answer, right here where it's got that 0.6 in the formula, so for this where we have the cell highlighted, its cell I8 is greater than or equal to 0.6. If you came up with a lower ratio answer, that's where you're going to make the change in the formula. Then the rest of it, it'll stay the same. And if it goes below that ratio answer, so if we'd have gone below 0.6, let's say our ratio was 0.59 or 0.4, we would have gotten the statement reobserve. And let's do that. So what we're going to do is we're going to change our latitude root mean square error to 0.011 and press enter. When we do that, notice that our min-max column went below 0.6, and we're given for our horizontal positional accuracy, we're given the statement, we need to go observe. And what's going on again is you're taking that elliptical error and you're trying to make it circular error, and based on that ratio value, it's saying that's not acceptable. Hopefully we have explained to you how the spreadsheet works to compute positional accuracy for OPUS rapid static reports. Calculating positional accuracy from RTK and VRS measurements. To begin, let's review RTK field procedures, and our RTK field procedures is where we would have two receivers. One is our base station with a radio transmitter, and then we have our another receiver, which is our rover that we use for measuring and staking out points. We typically go out and we set up our base station, hopefully on a known point. This could be maybe a NGS monument or some type of OPUS static or rapid static point, depending upon the type of job you're doing. Once we've gotten our base station set up, then with our rover, what we would want to go do and what we should be doing is going and measuring another control point. This could be a NGS monument or an OPUS static or rapid static point. And when we measure this point, we're recording and storing that point in the data collector, performing an inverse to make sure that we haven't set up on the wrong points, we haven't blown an HI, those common surveying mistakes. With the RTK out of the way, what happens when we go out in the field and we start using VRS? Well, with VRS, you've replaced that whole base station and radio transmitter, and now you've got cell phone surveying. One of the things that would be recommended would be to go ahead and, as you're on your way to a job site, if you have monuments near the job site, you would check into them. These could be an NGS monument, it could be an OPA static or rapid static point. Now, what do we mean by near the job site? That's where it's going to be your call as the surveyor to make on how far away do I get to check into these points to represent positional accuracy around my job site. If you've got a monument within a mile, you may find that acceptable. If you don't, I understand. If you have a monument within 10 miles, what's going to happen is you're probably going to check into that point, put the equipment in the truck, and drive 10 miles. You're probably not representing positional accuracy on that job site with your nearest monument 10 miles away. So how do we handle, or what's the best way to approach that type of scenario? Well, the first thing that would be recommended is if you have your nearest monument is, let's say, 5, 10, 15 miles away from your job site, the first thing that you'd want to do is possibly perform an OPA static or a rapid static solution, and then use your VRS to check into that. If everything works and checks, then you could use your positional accuracy from your static and rapid static solutions to put that on any type of seal or certifications for your maps. You may not have that luxury to be able to perform an OPA static or rapid static session for the particular job. What you could do as another alternative is you could get to the job site, you could set 2 points like we would set an azimuth pair. You would shoot the point in the morning, let's say. You'd shoot the points again in the, let's say, around noontime, and then we'd shoot the points again in the afternoon. And we would take and establish that control points coordinates through the multiple shots by averaging them together, and then we could compute positional accuracy from that. Remember, we want to run our checks with our GPS just like we would do if we were doing a total station or using robotic instruments to perform surveying. We got to set up that instrument, we got to take our back sight to make sure that everything is working correctly. Now, to compute positional accuracy from RTK or VRS measurements, we're going to use all of what we've talked about in Part 3 from the National Standards for Spatial Data Accuracy. What we're going to have to do is we are going to have to compute the root mean square error in northing and the root mean square error in easting, which means we've got to have coordinates for our control point, whether it's from a monument or a OPA static report. That would be our control coordinate points. Maybe you shot a point and averaged it together. Well, that averaged answer is what you would put in for N control and E control. And then when you check into that point as a separate shot, you've got N computed and E computed, so that's your check shot values. We've got to take each time we've done that, subtract it, square it. We'll add all the squared answers together. We'll then divide by the number of times we shot that point, and finally we'll then take the square root to get our root mean square error in northing and easting. Then we have to use the same scenarios. If our root mean square error is equal, we've got that 1.7308 times either the root mean square error in the northing or in the easting. It doesn't matter because the value is the same. Or we're going to have to perform our ratio test if our root mean square error is not equal by taking the smallest value, dividing it by the largest one, and if that ratio falls between 0.6 and 1, then we can use the accuracy formula of 2.4477 times 0.5 times the addition of our root mean square error in northing plus our root mean square error in easting. To compute our vertical positional accuracy, we'll use the same root mean square error formula where we'll have our vertical control point coordinates. We'll subtract the vertical computed coordinates that come from checking into that point. Each time we subtract it, we've got to square that answer. We'll add all the squared answers together, divide by the number of times we shot that point, and finally take the square root. Then to compute our vertical positional accuracy, it'll be 1.96 times the orthometric height. At a minimum, to compute your root mean square error, it requires multiple occupations on a control point. You've got to shoot your control point a minimum of 2 times to compute root mean square error. For your GNSS measurements, here's some really good recommendations. Whether you use an RTK, whether you're using VRS, ideally, you really want to have 4 hours between your check shots. The reason why is you get a different constellation of satellites overhead, which gives you a different set of measurement values, which should give you repeatability and reliability. At a minimum, you want 2 hours between occupations. If you sit there and you shoot that point 3 times in a row, more than likely your root mean square error that comes out and gets computed is either going to be really tight in the northing or really tight in the easting, and then the easting or the northing, the other answer will be skewed, and it'll be skewed so much that in the spreadsheet you're going to be given the statement to go back and re-observe. What we're going to do now is we're going to go through the spreadsheet, and there are 2 tabs we're going to concentrate on. We're going to do the RTK VRS accuracy monument check, and that monument check tab is where you've already got a known control point, whether it's an NGS monument, whether it's an OPUS static or rapid static point that you're checking into. And then the second tab is RTK VRS accuracy average. And the average one comes from you may not have time or you don't have the resources to set OPUS static or rapid static points, and you've determined that your closest monumentation is too far away to represent positional accuracy. What you're going to do is you're going to shoot that point in the morning, you're going to shoot that point, let's say at lunch, and then you're going to shoot it again in the afternoon, and you're going to average those shots together to come up with what you would publish out for the control point coordinates to be used on your project. We're going to go through both tabs, show you how they work in the spreadsheet. Computing positional accuracy from RTK and VRS measurements when you're checking into existing monumentation or control points. To follow along with the example here, what we did in the spreadsheet for you is we went ahead and left this sample instead of having you key it in. Let's go through it first and understand what's going on, and then we'll show you how to make modifications to the spreadsheet. We went out to the field, we used RTK or VRS, and our job was in metric. And we had existing coordinates of control point number 100, and that is what was typed in above the solid green line. We typed in the northing, easting, and elevation values of the control point number 100, and that's all you have to do. Then it automatically converted the metric answers to US survey feet and into international feet for us. Down below the green line is where we took the printed information of our check shots into point 100 and entered those in metric into the spreadsheet for northing, easting, and elevation as well. We shot our control point 3 times, and what the spreadsheet does is if you use your cursor and you click in the column under RMSE northing and it corresponds to the row for meters, if you look up here in Excel, we see our formula. We start off by doing a rounding statement, and this is to keep it to 3 decimal places, because if we don't, Excel will carry the numbers out to infinity and beyond. Then we're running the square root formula, and then we're doing an average of C3, and cell C3 is the northing control coordinate values, minus cell C7, which is our northing check shot values, and it's squaring it. And it's doing the same thing for cell C3, the control coordinate values, minus the check shot values for cell C8, it's squaring it. And then it's doing the same thing for cell C3, which is the control coordinate values, minus cell C9, our third check shot. It's squaring those and squaring it, adding it all together, square rooting it, running the round statement to keep it to 3 decimal places. So that's what goes on for computing your root mean square error in northing. The same formula is done for easting, and also the same formula is done as well for elevation also. What happens after our root mean square error has been computed? What we have to do is we have to determine if we have equal values for our root mean square error in northing and easting to properly compute our horizontal positional accuracy. If they're not equal, we have to use a different set of formulas to compute our horizontal positional accuracy. And then finally, from our elevation, we have to compute our vertical positional accuracy. We have our RMSE min over RMSE max column. That's our root mean square error minimum divided by our root mean square error maximum column. And what this does is it figures out which value is the smallest and divides it by the largest. That's what we've got going on here in this if statement. And then if we go over to the horizontal positional accuracy column, we've got the double if and statement, and it's saying if cell I3 is greater than or equal to 0.6, remember that was the ratios from part 3, between 0.6 and 1, we're going to use the formula that starts off with 2.4477. If it was equal to 1, which that's what it says if I3 equals 1 up here, we're going to use the formula of 1.7308 times, in this case it uses cell F3. If none of those statements are true, that's when we're going to get the reobserve statement to show up. Finally, for our vertical positional accuracy, we take our root mean square error in elevation and multiply it by 1.96. If you want to make modifications to your spreadsheet, let's say you're always going to work in survey feet or you're always going to work in international feet, what you can do is you can go over here to the units, you can change meters to survey feet or international feet, and then you could actually delete rows 4 and 5 out of the spreadsheet. Then down below, you could change the value here for meters to survey feet or international feet, and you can enter in your normal working units and the spreadsheet's still going to work the same. Let's say that you checked into a monument maybe 2 times, maybe 4 times, and if you do that, you're going to need to readjust some of the calculations that goes on for root mean square error. To do that, if you put your cursor in the root mean square error northing column, that corresponds to meters here. If you need to get rid of a specific calculation, notice here how we have C3 minus C9 in parentheses, and then the up arrow, which is our square root, and then the number 2, which is for our square value, excuse me. You would want to delete that out if you only had 2 observations. If you had more than 3 observations, you would want to repeat this by putting a comma after the 2 and then doing your formula of, let's say, C3 minus now C10. Close the parentheses, up arrow 2 again. So that's how you can adjust your root mean square error calculations, not only for northing, but also you would have to do it for easting, and you would also have to do it for elevation as well. Finally, if you have referenced some of the other documentation and based on your board rules and interpretations and rulings, if you feel comfortable in changing your ratio value from 0.6 to something less than that, right here where it says greater than symbol equal to, 0.6, that was where you would put in the new number. You would replace the 6 with, let's say, 0.4 or 0.5 based on your interpretation and what your board rules will allow you to do. We now have learned how to work with the spreadsheet for computing positional accuracy when you're using RTK or VRS measurements and you're checking into monuments or control points. Computing positional accuracy from RTK or VRS measurements, where you're going to go out into the field and you're going to shoot a point multiple times. You're then going to average the shots together to come up with your control point answers. We're then going to show you how to compute positional accuracy from that. What we're first going to do is we're going to describe what the spreadsheet is doing, and then we're going to go in and show you how to make modifications for your own use. Instead of having you type in everything, we went ahead and pre-filled this in. What we did is we went out into the field and we shot a point multiple times. The job was in metric, and we shot our point 3 times. So what's going on above the green line is the only thing you have to enter in. We entered in our shots for point number 100. We entered in its coordinates, point 101 and 102. We entered in the northing, easting, and elevation. That's the only thing you have to enter in. Then down below the green line, what the spreadsheet automatically does for you is it automatically computes the averaged coordinates in meters for northing, easting, and elevation. It did it in meters in this case, and it automatically has converted it over for us into survey feet and international feet. So our averaged values here in the averaged row for our northing, easting, and elevation is now becomes the control points coordinates that we would use. Then what the spreadsheet does is it goes ahead and computes the root mean square error in northing, easting, and elevation. And it does it here. We have to first use a rounding statement, and we're rounding off to 3 decimal places, because if not, Excel will carry the decimal places way beyond what we'll ever need for. And what it does, as we look, it's doing the square root, and then it's doing the average. It's taking cell C7, which is now our control point northing coordinates, and it's subtracting it from cell C3, which is one of our shots on that point. It's then squaring that answer. It's doing the same thing for the second shot and the third shot, and it's squaring each one of those answers. It's then averaging those answers together, taking the square root and rounding it off to 3 decimal places. It does the same thing for easting, and it also does the same thing for elevation as well. Then, once you've done that, the spreadsheet automatically keeps computing your horizontal and vertical positional accuracy. And remember, to compute your horizontal positional accuracy, we first have to look and see whether our root mean square error in northing and easting is equal or is not. And that's where we have the column of RM SE min over RM SE max. And we can see here with our if statement, we're figuring out which is the smallest one, and we're dividing it by the largest one to get our ratio answer. Since our root mean square error is equal, when we go over to compute our horizontal positional accuracy, we've got our if statement. The first part of the if statement looks to see if that min-max column falls between 0.6 and 1. If so, it uses the 2.4477 formula. If it's equal to 1, then it uses the 1.7308 formula. And if none of that is true, then it's going to give us the statement here to reobserve that point. Finally, as we go over to our vertical positional accuracy, it takes our elevation, root mean square error, and multiplies it by 1.96. Now, if you want to make modifications for your own use, let's say you're going to work only in survey feet or in international feet, and you may have to change how many times you shot the point, here's how you can do it. you can go ahead and replace the units with your nominal units, survey feet or international feet, and you would change that here as well below the green line, and then you would delete just the rows 8 and 9 to get rid of those values, because you're not going to need them, because it's going to multiply things and blow it up on you. If you only, let's say for your average, you shot it in the morning and you only shot it in the afternoon, so you only had 2 observations, or you had 4 or 5 observations, where you're going to have to make your change is in the calculation of your root mean square error. And to show you that, when we click on our root mean square error calculation for the northing, is if you wanted to only have 2 shots, you would delete the, let's say, C7 minus C5 with the up arrow 2 beside of it. You would delete that in the corresponding comma to the left of it. If you needed to add more check shots to it after the 2, you would put a comma there, and then you would go ahead and keep repeating the same formula. So it'd be, let's say, C8 minus C9 or something like that to make your formula work right. Don't forget the up arrow 2 for the squaring. So this is how you can modify your spreadsheet, as well as understand how it works to compute positional accuracy from RTK and VRS measurements when you're going to go out and shoot it multiple times and then come up with your average solution or your average coordinates.